Hey everybody, and welcome back to Linear Algebra Online. So the plan for today is talk about the beginnings of a really important idea in linear algebra called diagonalization and similarity. And this stuff is used all over the place, and it shows up a lot in a lot of applied math because it's one of these areas where computationally it's going to be much easier to do some stuff if you can first diagonalize a matrix. And it turns out that if you can do this given very special matrices and all that, some of the properties of the original matrix, like A, and a diagonal one that comes from it, are what we call invariant, and they don't change after that. The properties of one are sort of in both matrices, and it's easier to work with a simpler diagonal matrix sometimes than a regular kind of matrix with entries all over the place. So it's one of these things that kind of gets its motivation from a complexity standpoint. But there's lots of other reasons too why we would want this, and it helps us prove some results in math and things like that too, which we'll see. But so hopefully you watched, I wanted you to watch Grant's video with the end of the eigenvalues and eigenvector stuff, where he talks briefly about the powers of matrices, and that's just another example. How it's much easier if you have a diagonal matrix D, the powers of that are really easy to compute versus the powers of a matrix A. And you'll see examples where that kind of comes up here, and how that's just another computationally easier problem. If you can get this matrix D, which relates to A very specifically, then in order to do A to a power, you can actually end up doing D to a power with a little bit of other work. But so they're just nice. And the more you study them, the more you'll kind of see why they're so nice. But this is the formal definition. So A is diagonalizable if there basically is a diagonal matrix D such that A is similar to D. And that means that there needs to be an invertible n by n matrix P such that P inverse AP is equal to D. So this definition similar is really given there too, but I have it on the next slide as well. But just so I kind of have it here too, the notation is that A, we do a tilde, A is similar to D. And really the name does imply what's going on. These two matrices, if you can create this constructed sort of setup here, where this is diagonal and this is invertible matrix P, then these two matrices are very closely related. And a lot of stuff are going to basically be transferred between either one. I talk about rank, eigenvalues, invertibility, stuff like that. So it's always going to be nice in math if instead of working with a complex matrix or something, you can work with a simple diagonal one. So a lot of times we do this and then just work with that rather than working with this messy thing. So this is the formal definition of similar, which just says that if so A is similar to B if there is an invertible matrix P such that this P inverse AP equals B. And then I said it before, but this is the notation for similar. Sometimes you'll see this written as there's an invertible matrix P such that AP equals PB. So all I did there is I multiplied by P on the left. So sometimes we see that one. And this one could be a little nicer because you don't have to find an inverse. So if that way you only check you do a multiplication here with a matrix and a multiplication in here. And if they're equal, then they're similar. Okay. And there's some nice properties, and you might recognize some of these properties. And I want to actually go through the proofs of these because I think they're kind of good to see, and they will kind of show some techniques that we'll use a lot for working with similar and diagonalizable matrices and things like that. So the first one is that a matrix like A is similar to itself. And to do that, we just need to find, so if there is a matrix P that does this thing. And so you just need to find one, and you can definitely find I is invertible, right? So if you just set up I inverse AI, and clearly that equals A, you're good. That's literally all you have to do. You just have to find a matrix that does it, and that's by definition means that A is similar to A. All right. So this one says that if A is similar to B, then B should be similar to A. So if A is similar to B, then I think I'm going to do this kind of up here. So if A is similar to B, then by definition there exists some invertible P such that we get this P inverse AP equals B, right? And then we can just multiply, like on the left by P. Likewise, if you multiply on the left by P, right, you're going to kill the inverse there. Then we'll get AP equals PB, right? Or multiply on the right by P inverse and get A equals PB P inverse. And it's really close to being in the right format, but we need the inverse here on the left. And so this is just kind of like it feels a little cheap, but you can do this. So we can just say define like Q or something as P inverse. So Q inverse would equal P inverse inverse, which is P. And then A would equal Q inverse BQ, right? Which by definition implies that B is similar to A, right? So when we have this structure, this is what that says by definition is that the thing inside is similar to the thing on the outside here. A is similar to B. And so now the thing inside B is similar to A. So these two are the first parts right here that I wanted to prove. And then this last one, it's saying if A is similar to B, B is similar to C, then you should have A is similar to C. And this is that like transitivity property in math. And so I want to prove that one too. All right, so here, this is all the stuff I have to work with in the beginning. So A similar to B implies there exists some P and P inverse such that P inverse AP is B. Likewise, B similar to C implies like there exists some, we'll go Q and Q inverse such that Q inverse, whoops, not A anymore, I'm looking at my line above, Q inverse BQ equals C, okay? And then basically I'm going to do substitution. So I have an expression for B up here. I'm going to substitute in. So that means that we have Q inverse P inverse A. Here, well, actually, maybe I'll try this with colors here. So we got Q inverse from the purple line, right? And then we've got B is, in the green part up there, is P inverse AP. This is like what I'm substituting, times Q, right, equals C. And I'm also going to say note that Q inverse P inverse would equal PQ inverse via just inverse like properties, right? And then we basically have it because we're just going to say like note. Then we have PQ inverse APQ, right, equals C. And we just let, I don't know, R equal PQ. So R inverse AR equals C. And thus, by definition, A is similar to C, as we wanted to show. So these are just kind of good, I think, examples to show like the kind of structure of how we use the definition of like a diagonalizable matrix and similar. Well, no, we haven't used diagonalizable. We've used just similar. So the only difference with this, with diagonalizable, is that like the C here would be a diagonal matrix instead of just, right now it's not necessarily diagonal matrix. It's just like arbitrary one. So diagonalizable is like a more special version of this, basically. So those properties actually that we just did are really famous in math. The first one was actually called the reflexive one. And then the one that kind of goes back and forth, like A similar to B similar to A, is symmetric. And then the last one, I think I already said, is transitive. And anything in math that satisfies all three of those is what we call, is this color, an equivalence relation. And equivalence relations are really, really nice. And I'm going to write here. Items that do this in math are very useful. One of the key things in math is to actually try to classify a lot of things. And if you can show that there's like an equivalence relation between two items, it helps you kind of categorize those as being structurally sort of the same thing. And you can go down like a huge rabbit hole, and I have examples here of like all sorts of things that are equivalence relations. There's a lot of things that are not equivalence relations too. But basically it kind of helps us show, it's like a very important classification of different things. So if we take like this one, so is congruent to mod n on the integers, what that is basically saying, modulo n. So if you take like a clock, like that has only, a finite number of numbers. We don't just keep counting, like once we get to, the top of the clock, it resets. And that's an example of something that has only 12 different numbers in it. And there's things like binary that has only two numbers, a 0 and a 1. And these things, there's a lot of things in the world that maybe it's not just 0 and 1, but there's only two unique things to that set. And we could form an equivalence relation between, say, binary and another thing that just has two items in it. And so structurally, those two things are basically behave the same. That's what this would mean. And the way you prove it is you literally do what we just did here. You would need to go through and like prove all three of those properties. So we just proved that similarity of matrices is an equivalence relation. So if you have two matrices that are similar, then they're structurally about the same thing. That's kind of the idea. It helps us classify them, which is really useful in math. So this theorem right here is basically just saying that if you have two matrices that are similar, okay, then all of these things are happening. That basically the determinant of one is just equal to the determinant of the other one. That if one is invertible, if and only if the other one is invertible, they're going to have the same rank, they have the same characteristic polynomial, same eigenvalues. A to any power is similar to b to any power for all integers greater than or equal to 0. And if a is invertible, then a to that some power greater than or equal to 0 is similar to b to that power for all integers. So it's more kind of powerful statement. So it's not just for positive integers, or non-negative integers. But these are just an example, right, of what the power and similarity is. If we can show that two matrices are similar, all of a sudden we have a ton more info about one matrix if we know something about the other one. And that's what all equivalence relations kind of are getting at, is basically getting more information by classifying things together and being like, okay, there's an equivalence relation between these things. So, I'm getting info about another group or another set just based on knowing something about original one, assuming that you can build that equivalence relation between them. So it's a very common goal in a lot of high-level math, is to try to build these equivalence relations and show that two things are kind of structurally the same thing. So I actually want to go through and prove these, and they're some of them are pretty quick, but I think they're all good examples, and they all use similarity somewhere. So I wanted you to kind of see them. So really, I'm not going to write it every time, but I'll write it up here. So if A is similar to B, the one thing that I basically have to work with, right? So you can see, it right here, all of a sudden this stuff is what we got to show. But what I have to work with is that P inverse AP, right, equals B. That's basically what I got every single time, all right? And, so let's just jump into this thing. So for A, the determinant of B, so I'm basically just going to take the determinant of both sides, equals the determinant of P inverse AP, all right? But we have a property with determinants that is in a previous video, where a determinant of a product is just the product of the determinants. So this is going to be equal to the determinant of P inverse times the determinant of A times the determinant of P. And there's another property that the determinant of P inverse is really just 1 over the determinant of P. And so I'll just copy the rest of this down. And then you can see, right, this right here is going to cancel with that part. And so you truly get determinant of A, which is what we want to show. Determinant of B is equal to determinant of A. All right, so for B, all right, so B is pretty quick once you have A, actually, which we've proved, so we can use. And this is basically all it is. So we know that A invertible happens if and only if determinant of A is non-zero. And A similar to B implies the determinant of A equals the determinant of B. So determinant of B must also not be 0, right? Therefore, B is invertible, right? And like all of these are really if and only ifs. Like A invertible if and only if determinant of A doesn't equal 0, and equals is like an if and only if. So this is we also have like determinant of A equals this if and only if. Well, yeah. So this is an if and only if. This is an if and only if down here that's split up into two different sentences. But so really it does prove that as like a bijection. All right, so for C, we know basically that the dimension of the column space of like A is equal to the rank of A. And we know that there's this connection, right, with the rank nullity theorem between the rank, column space, row space, whatever way you want to think of it, and the null space. And so if you can actually show the null space of A and B are the same, then you've shown that the rank of A and B are the same just by the rank nullity theorem. So a lot of times we do it that way because it's much easier to work with something set equal to 0 rather than trying to work with like the column space or the row space of a matrix. So even though we have this, we're going to basically use the fact that the rank of A plus the nullity of A equals n for whatever that, for an n by n matrix. And then we know that if these two things for A and B are the same, then these two things are the same because A and B have the same size. All right, so I'm going to start and I'm going to just say let X be in the null space of A. So AX equals 0. All right. And then we know that A is similar to B. So therefore, basically I'm just going to, I am going to use I'm going to rewrite A as P inverse BP is my A now, times X, and that still should equal 0. And then P inverse exists, right? So if I multiply on the left by P inverse, I would have BP X equals 0. And then basically what I would just do is then note PX is a vector in the null space of B now. Note. And so this shows that the null space of A gets us contained in the null space of B. Okay, and then we can do kind of a similar thing. So now I'm just going to do this. Let V be in the null space of B. So BV equals 0, or P inverse AP, right, which is my B, times V equals 0. Okay, and then I'm going to do the same kind of trick where I multiply on the left by P inverse. And so I can get hence like A P V would equal 0. And so I'll do the same kind of trick. I can group this part, right? And so we get that the null space of, we started in B, is contained now in the null space of A. And whenever we do this kind of thing where we have both containments, basically, I'm trying to save myself some room here, but this, right, and those two containments basically imply that null space of A equals null space of B. So by the rank nullity theorem, the ranks are equal. So just enough room. But that's the idea on that one. Basically, common trick is just to work with the null space instead of the rank because it's typically a much easier thing. All right. So D just involves the characteristic polynomial. And so here, we basically just start with one of these. So we can start with, we'll just start with determinant of B minus lambda I. And we just, we have an expression for B, and we're going to plug it in. So this one you can kind of just do with an equation. So this will just be equal to the determinant of then P inverse AP minus lambda I, right, which is my similar part, which we could say is equal to P inverse AP minus lambda. And then this might seem kind of weird, but it's one of these things where you'll kind of see where it's going after I do it. But the identity is similar to itself. So there should be, so it's like you can say, let me just close this off. So this is true, right? I can just, stick P inverse P in here, which you can just think of it as like, you can actually commute, right, with the identity. So I'm basically putting like P inverse P right next to each other, which is the identity, and multiplying by 1. And then I'm just like splitting it up and commuting things, and that's okay to do. But then that's nice because it gives me a P inverse that I can basically factor out. And so if I do that, I'm going to get determinant of, because I can move the lambda like in here. So that's okay because it's just a constant. So then I have P inverse pulled out times A minus lambda I, and then times P, right? And now I've got a product of a bunch of matrices where I can use the determinant property, and that would be equal to determinant of P inverse, determinant of A minus lambda I times determinant of P, right? And this is nice because this and this cancel, because this one's 1 over determinant of P. And so then we have it, right? Determinant of B minus lambda I is equal to determinant of A minus lambda I. So their characteristic polynomials are the same, which is nice. So for this one, I'm just going to start with, B equals P inverse AP again. Or likewise, BP inverse equals P inverse A, if I just move things around a little bit. And then we're going to let lambda be an eigenvalue with corresponding eigenvector x. All right, so I'm going to take this and multiply on the right by x. So PB inverse x would equal P inverse AX. But x is an eigenvector. So PB inverse x equals P inverse lambda x, right? If I just substitute that part out. And then I could take my lambda out, like move that around because it's a constant. And if you look at this, right, if I group it here and here, right, then we see that, P inverse x is an eigenvector for B, but has eigenvalue lambda still. And that's the part that we wanted to show. It doesn't matter that it's a different eigenvector. We just want to show that they have the same eigenvalues. And I realize I'm running out of time, and instead of probably doing a whole nother video for one little extra part, I'm just going to put down F, and G is pretty similar. So honestly, it uses a lot of part F. So I'm just going to put down F, and you'll kind of, I think, see how G would work from there. All right, so this is basically the idea for the part F. So it's an induction problem, and the base case is really straightforward. A is similar to B was just given, so we have that. And then we assume it holds for K and show it holds for K plus 1. And basically, if you just use the definition of similarity, like A similar to B here, then if you start with B times B to the K, right, here's my B, right? And here's my B to the K by the induction hypothesis. In here, you get some nice stuff happening because you get these inverses to kill each other off. So then you have that, and that multiplies to A to the K plus 1. And so you've got it because, this is B to the K plus 1. And the last one, if it's invertible, then there's an inverse part that can happen, and it's going to allow you to get negative powers up here as well. So it's really very similar to this. You just have negative numbers because of the inverse part.